Picture this: a vast, pitch-black void stretches endlessly in every direction, dotted with billions of galaxies, each containing billions of stars. Yet, despite all our technological advancements and centuries of scientific inquiry, there are questions about space that leave even the brightest minds scratching their heads. What lies beyond the edges of our observable universe? Are we truly alone in this cosmic expanse? And what exactly is dark matter, the invisible force that seems to hold galaxies together? These are just a few of the mind-bending questions that remain unanswered, mysteries that continue to spark curiosity and ignite the imagination. In this video, we're diving into 20 of the most perplexing questions about space that no one yet can answer. From black holes to parallel universes, these cosmic enigmas challenge our understanding of reality itself. So, buckle up and get ready to explore the unexplored. Who knows, by the end of this journey, you might just find yourself with more questions than answers. Let's begin. Now shifting our gaze to the edges of what we can see, let's explore the first of our 20 questions. What lies beyond the observable universe? The observable universe is everything we can detect with our telescopes and instruments, a sphere around us that stretches roughly 93 billion light-years across. But here's the thing, that's not the entire universe, it's just the part we can observe. So, what's out there beyond that? Scientists have theories, but no definitive answers. One possibility is that the universe extends infinitely, with galaxies and stars continuing forever in all directions. Another fascinating idea is the multiverse theory, which suggests that our universe could be just one of countless others, each with its own unique laws of physics. But how could we ever know for sure? The truth is, we're limited by the speed of light. Anything beyond the observable universe is currently out of reach, because light from those regions hasn't had enough time to reach us since the Big Bang. This makes the question not just a matter of curiosity, but a fundamental challenge for cosmology. As we push the boundaries of our understanding, the mystery of what lies beyond remains one of the most profound and humbling questions in all of science. Now venturing into the realm of the unknown, let's tackle our second question. Are we alone in the universe? The universe is unimaginably vast, with billions upon billions of stars and planets scattered across its expanse. With so many possibilities, it seems almost impossible that Earth is the only planet harboring life. This brings us to the Fermi Paradox, which poses a simple yet profound question. If the universe is so enormous and filled with potential for life, why haven't we found any evidence of it? One of the first attempts to address this question was through the Drake equation, a formula designed to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. While the equation provides a framework, many of its variables, like the likelihood of life developing on a planet or how long civilizations survive, remain highly speculative. Adding to the complexity is the sheer scale of the universe. Even if intelligent life exists, the distances between stars and galaxies are so vast that communication or travel across them would be incredibly challenging with our current understanding of physics. Then there's the issue of detection. Our methods for searching for extraterrestrial life, like listening for radio signals or analyzing distant planets' atmospheres, are still in their infancy. While we've made strides with projects like SETI, the search for extraterrestrial intelligence, we've yet to find definitive proof. Some scientists argue that advanced civilizations might be so different from us that we wouldn't even recognize their presence. Others suggest that civilizations might self-destruct before they can make contact, adding a layer of urgency to our own survival. So, as we continue to scan the cosmos and refine our technologies, the question of whether we're alone remains one of the most compelling mysteries of our time. Now turning to another profound cosmic mystery, let's explore the enigma of dark matter. Dark matter is one of the most puzzling components of our universe, making up an astounding 85% of all matter, yet it remains invisible to us. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it undetectable by traditional telescopes. So how do we even know it exists? The answer lies in its gravitational effects. Scientists first inferred the presence of dark matter by observing how galaxies rotate. The outer regions of galaxies move at speeds that can't be explained by the visible matter alone, suggesting an unseen force, dark matter holding them together. It also plays a crucial role in the large-scale structure of the universe, influencing how galaxies cluster and move. Despite its importance, we still don't know what dark matter is made of. Theories range from weakly interacting massive particles, known as WIMP, to hypothetical particles like actions. Researchers are conducting experiments deep underground, where they hope to detect the faint signals of dark matter particles interacting with ordinary matter. Projects like the Large Hadron Collider are also searching for clues by recreating high-energy conditions similar to the early universe. Yet, despite decades of effort, dark matter continues to elude us. Its discovery would not only solve one of the greatest mysteries in physics, but also reshape our understanding of the cosmos. As scientists push the boundaries of technology and theory, the hunt for dark matter remains one of the most exciting and challenging quests in modern science. As we delve into the next cosmic puzzle, let's turn our attention to dark energy, a force even more mysterious than dark matter. While dark matter's gravitational pull shapes the universe, dark energy is responsible for something even more profound: the accelerating expansion of the cosmos. Discovered in the late 1990s through observations of distant supernova, dark energy is now believed to make up roughly 68% of the universe's total energy. But what exactly is it? The truth is, we don't fully know. Dark energy appears to act as a sort of repulsive force, pushing galaxies apart at an ever-increasing rate. One leading theory suggests it's a property of space itself, often referred to as the cosmological constant, a concept introduced by Albert Einstein. Another possibility is that dark energy is a dynamic field that changes over time, known as quintessence. Despite these theories, the true nature of dark energy remains one of the biggest questions in modern science. Understanding it could shed light on the ultimate fate of the universe. Will it continue to expand indefinitely, or will dark energy eventually weaken or evolve? Scientists are using powerful tools like the Hubble Space Telescope and the upcoming Nancy Grace Roman Space Telescope to map the universe's expansion and gather clues about dark energy's behavior. Yet, with every discovery, new questions arise. Dark energy reminds us that the universe is full of surprises, and unraveling its secrets may require entirely new ways of thinking about physics and reality itself. Now shifting our gaze to the very beginning of everything, let's explore the origins of the universe itself. The most widely accepted explanation is the Big Bang theory, which suggests that the universe began as an unimaginably hot and dense point nearly 13.8 billion years ago. In a fraction of a second, this tiny point expanded explosively, setting the stage for the cosmos we know today. But while the Big Bang is our best framework for understanding the universe's birth, it doesn't answer all the questions. For instance, what triggered this colossal expansion? What existed before it, if anything? Some scientists propose that the Big Bang wasn't the absolute beginning but rather a phase in a much larger cosmic cycle. Others delve into quantum physics, suggesting that the universe could have emerged from a fluctuation in a pre-existing quantum field. Then there's the question of what caused the conditions for the Big Bang to occur in the first place. Was it a random event, or is there a deeper yet undiscovered mechanism at play? These mysteries remind us that even our most advanced theories are incomplete. The Big Bang isn't just a single moment in time, it's a doorway to a series of profound questions about existence itself. As we continue to study the universe's earliest moments through tools like the cosmic microwave background radiation, we're not just looking for answers, we're trying to uncover the very rules that govern reality. And with every discovery, we're reminded that the story of the universe is far from finished. Now venturing into one of the most mysterious realms of the cosmos, we confront the enigma of black holes. These cosmic phenomena, born from the collapse of massive stars, are regions of space where gravity is so intense that not even light can escape. At the heart of every black hole lies the singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding the singularity is the event horizon, the boundary beyond which nothing can return. Crossing it would mean being forever trapped in the black hole's grip. But what happens inside the singularity itself remains a puzzle. It's a place where space and time cease to exist as we understand them, and our current theories of gravity and quantum mechanics clash. Some scientists suggest that the singularity might not be a point but a ring-like structure, opening the door to wild ideas like wormholes leading to other parts of the universe. Then there's the information paradox, which questions what happens to all the matter and energy that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but black holes seem to defy this rule. Stephen Hawking proposed a groundbreaking idea called Hawking radiation, suggesting that black holes aren't entirely black. Over immense periods of time, they emit tiny amounts of energy, slowly evaporating. This raises even more questions. Where does the information go? Some theories, like the firewall hypothesis, suggest that a fiery wall of energy might exist just inside the event horizon, destroying anything that crosses it. Others argue that the information is somehow encoded in the radiation itself, preserved in a way we don't yet understand. Black holes continue to challenge our understanding of the universe, blending the bizarre with the profound. They're not just cosmic vacuum cleaners, they're windows into the deepest mysteries of physics. As we study them through tools like gravitational wave detectors, we're not just exploring black holes, we're testing the very limits of our knowledge. And with every discovery, we're reminded just how much remains to be uncovered in the vast, uncharted depths of space. Shifting our focus to another cosmic puzzle, we now explore the tantalizing question: is time travel possible? The idea of traveling through time has captivated human imagination for centuries, from science fiction stories to scientific theories. But could it ever be more than just a dream? Let's examine this concept through the lens of general relativity and quantum mechanics, two pillars of modern physics. Albert Einstein's theory of general relativity suggests that time and space are deeply intertwined, forming a flexible fabric known as spacetime. Massive objects like planets and stars warp this fabric, creating what we experience as gravity. This warping also opens up intriguing possibilities for time travel. One such possibility is the existence of wormholes, hypothetical tunnels through spacetime that could connect two distant points in space and time. If traversable wormholes exist, they might allow for shortcuts not just across space but also across time. However, wormholes remain purely theoretical, and their stability would require exotic matter with negative energy, something we've yet to discover. Another fascinating idea comes from the concept of closed time-like curves. These are paths through spacetime that loop back on themselves, allowing an object or person to return to their own past. Some solutions to Einstein's equations, like the Gödel universe, suggest that closed time-like curves might exist under certain conditions. But here's the catch: such scenarios often rely on extreme and unrealistic conditions, like infinitely long rotating cylinders or the presence of cosmic strings. Quantum mechanics adds another layer to the puzzle. At the quantum level, particles can exhibit strange behaviors like entanglement and superposition, which seem to defy our everyday understanding of time. Some interpretations of quantum physics even suggest that particles might travel backward in time, though this remains a controversial and speculative idea. While time travel remains a theoretical possibility, it's important to note that no experimental evidence supports its feasibility. The energy requirements, the stability of wormholes, and the paradoxes that time travel might create, like the famous grandfather paradox, present significant challenges. Yet, scientists continue to explore these ideas, pushing the boundaries of our understanding of time and space-time. So, is time travel possible? For now, it remains one of the great unsolved questions of physics, blending the realms of science and imagination. As we continue to probe the mysteries of the universe, who knows what incredible discoveries might lie ahead? Next, we'll turn our attention to another cosmic mystery, the fate of the universe itself. Now delving into one of the most profound questions in cosmology, let's explore the ultimate fate of the universe. What lies ahead for the cosmos? Scientists have proposed several compelling theories, each painting a different picture of how the universe might end. These scenarios, the Big Freeze, the Big Crunch, and the Big Rip, are shaped by the mysterious forces of dark energy and dark matter, which continue to influence the universe's expansion and structure. First, consider the Big Freeze, also known as the heat death scenario. In this theory, the universe continues to expand forever, driven by dark energy. Over trillions of years, galaxies will drift farther apart, stars will burn out, and the universe will grow colder and darker. Eventually, all matter and energy will become so spread out that no new stars or galaxies can form. The cosmos will reach a state of maximum entropy where no usable energy remains, leaving the universe in a cold, lifeless void. In contrast, the Big Crunch offers a dramatically different outcome. If the gravitational pull of dark matter and ordinary matter eventually overcomes the repulsive force of dark energy, the universe's expansion could slow, stop, and reverse. Galaxies would begin to move closer together, temperatures would rise, and the universe would collapse into a single, infinitely dense point, a mirror image of the Big Bang. This cyclical model suggests that the universe could be part of an endless loop of expansion and contraction, though evidence for this scenario remains elusive. Then there's the Big Rip, a more violent end to the cosmos. In this theory, dark energy doesn't just drive the universe's expansion, it accelerates it to such an extreme rate that it eventually tears apart everything. Galaxies, stars, planets, and even atoms would be ripped apart as the expansion outpaces the forces holding matter together. This catastrophic end would leave the universe as a collection of isolated particles, unable to interact or form new structures. Dark energy plays a central role in determining which of these fates awaits the universe. Its repulsive force counters gravity, shaping the rate of cosmic expansion. Yet, its true nature remains one of the greatest mysteries in science. Similarly, dark matter, which makes up most of the universe's mass, influences how structures form and evolve. Together, these invisible forces hold the key to understanding the universe's destiny. So, what is the fate of the universe? While we don't yet have a definitive answer, each theory offers a glimpse into the possible futures of our cosmos. As we continue to study dark energy and dark matter, we may one day unravel this cosmic mystery. For now, the question of how the universe will end remains a profound and humbling reminder of the vastness and complexity of the cosmos. Next, we'll explore another enigmatic phenomenon, the origins of fast radio bursts. Now shifting our gaze to another cosmic enigma, let's uncover the mystery of fast radio bursts. These fleeting, incredibly powerful bursts of radio waves last only milliseconds, yet they release as much energy as the sun does in days. First detected in 2007, fast radio bursts have since puzzled astronomers with their unpredictable nature and immense energy. Originating from distant galaxies billions of light-years away, these bursts appear randomly across the sky, making them incredibly difficult to study and even harder to predict. So, what could be causing these bursts? Theories abound, ranging from the dramatic to the speculative. some scientists suggest they could be linked to highly magnetized neutron stars, known as magnetars, which emit intense bursts of energy as their magnetic fields suddenly shift. Others propose more exotic possibilities, such as collisions between dense objects like neutron stars or black holes. There's even speculation that these bursts could be artificial in origin, perhaps signals from advanced extraterrestrial civilizations. While this idea captures the imagination, there's no concrete evidence to support it, leaving the true origin of fast radio bursts shrouded in mystery. The challenge in understanding these bursts lies in their brevity and unpredictability. Unlike other cosmic events that can be observed over longer periods, fast radio bursts vanish almost as quickly as they appear, leaving astronomers with only a fleeting glimpse to analyze. Additionally, their immense distance means the signals we detect have traveled billions of years through space, potentially being altered by intervening matter, making it even harder to pinpoint their sources. Despite these challenges, advancements in technology are slowly shedding light on this phenomenon. New radio telescopes with faster data processing capabilities are now being deployed, allowing scientists to detect and study these bursts in greater detail. For example, the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, has detected hundreds of fast radio bursts since its launch, significantly expanding our understanding of their properties and distribution across the cosmos. Yet, even with these strides, fast radio bursts remain one of the most elusive and perplexing mysteries in astronomy. Each burst raises more questions than answers, fueling both scientific curiosity and public fascination. What triggers these intense explosions of energy? Could they reveal new physics or even hint at extraterrestrial intelligence? For now, these questions remain unanswered, but as technology advances and our understanding deepens, we may one day unlock the secrets of these enigmatic cosmic signals. Next, we'll explore the intriguing concept of parallel universes and the multiverse theory. Now turning to one of the most mind-bending questions in modern science, could there be parallel universes? The idea of multiple universes existing alongside our own has fascinated thinkers for decades, but it's not just science fiction, it's a serious topic in both quantum mechanics and cosmology. So, what do we really know about the multiverse? At the heart of this concept is the idea that our universe might not be the only one. Instead, it could be just one of countless others, each with its own set of physical laws and realities. One of the leading theories comes from quantum mechanics, which suggests that every time a decision is made or an event occurs, the universe splits into multiple branches. In one version, you might be watching this video, while in another, you're doing something entirely different. This is known as the many worlds interpretation, and while it's still debated, it offers a fascinating way to think about the nature of reality. Cosmology adds another layer to this idea with the concept of eternal inflation. According to this theory, our universe is just one bubble in an infinite cosmic foam. Each bubble could have its own unique properties, from the strength of gravity to the types of particles that exist. This means that somewhere out there could be universes where stars burn forever or where time flows backward. The possibilities are as endless as they are staggering, but how could we ever prove the existence of parallel universes? The truth is, it's incredibly difficult. By definition, these universes would exist beyond our observable reach, making them nearly impossible to detect directly. However, some scientists believe that subtle clues might be hidden in the cosmic microwave background radiation, the afterglow of the Big Bang. If we ever find anomalies that can't be explained by our current understanding of physics, it could hint at the presence of other universes. The multiverse remains one of the most speculative yet tantalizing ideas in science. It challenges our understanding of reality and forces us to ask, what does it mean to exist? Are we just one version of an infinite number of possibilities? While we may not have answers yet, the pursuit of these questions pushes the boundaries of human knowledge and imagination. Next, we'll explore what caused the Big Bang and the mysteries surrounding the birth of our universe. Shifting our focus to the very beginning, we now unravel one of the most profound mysteries in cosmology. What caused the Big Bang? This question takes us back to the origin of everything we know, yet it remains one of the greatest puzzles in science. The Big Bang theory describes how our universe expanded from an extremely hot and dense state, but what set it all into motion? At the core of this mystery lies the concept of quantum fluctuations. In the strange world of quantum mechanics, particles constantly pop in and out of existence, creating tiny ripples in the fabric of reality. Some scientists believe that a quantum fluctuation in a pre-existing void could have triggered the Big Bang, acting as the spark that ignited the universe. This idea suggests that our universe might have emerged from almost nothing, a thought that is as intriguing as it is mind-bending. Another leading theory is cosmic inflation, which proposes that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. This rapid expansion could have smoothed out the cosmos and created the conditions for galaxies to form. But what caused inflation to start in the first place? Some speculate that it was driven by a mysterious field of energy, often referred to as the inflaton field. While this theory explains many observations, the true nature of this field remains unknown. Adding to the complexity is the question of what, if anything, existed before the Big Bang. Was there a previous universe that collapsed and gave rise to ours? Or are we dealing with a timeless, cyclical process? These ideas push the boundaries of our understanding and challenge our very notion of beginnings and endings. Despite decades of research, the cause of the Big Bang remains elusive. The problem is that our current laws of physics break down at the extreme conditions of the Big Bang, leaving us with more questions than answers. This makes it one of the ultimate frontiers of human knowledge, a question that not only probes the origins of the universe but also the limits of our scientific understanding. As we continue to explore this cosmic mystery, we're reminded of how much there is still to discover. Coming up next, we'll dive into the enigmatic concept of cosmic strings and their potential role in shaping the universe. Shifting our gaze to another fascinating cosmic enigma, let's now explore the mysterious concept of cosmic strings. These theoretical structures are thought to be incredibly thin, one-dimensional filaments of energy stretching across the universe like cosmic spiderwebs. They are remnants from the early moments after the Big Bang, when the universe underwent rapid changes in its fundamental properties. Imagine the universe cooling and transitioning from a chaotic, high-energy state to a more stable one. Cosmic strings could have formed during this process, much like cracks forming in ice as it freezes. But what makes cosmic strings so intriguing is their potential role in shaping the universe's large-scale structure. Some scientists believe they could have acted as cosmic seeds, influencing the way matter clumped together to form galaxies and galaxy clusters over billions of years. Their immense gravitational pull could have created ripples in space-time, leaving behind a faint but detectable signature in the cosmic microwave background, the afterglow of the Big Bang. This has led to ongoing searches for evidence of their existence, though so far they remain purely theoretical. Detecting cosmic strings is no easy task. They are hypothesized to be incredibly thin, thinner than an atom. Yet they could stretch across vast cosmic distances, potentially even spanning the entire universe. If they exist, they would be incredibly dense, packing a tremendous amount of mass into their thread-like forms. This combination of extreme thinness and immense density makes them nearly invisible to our current observational tools. However, there's hope that future advancements in technology, such as more sensitive telescopes and gravitational wave detectors, might finally shed light on their existence. The study of cosmic strings isn't just about finding these elusive structures, it's about understanding the early universe and the forces that shaped it. If discovered, they could offer crucial insights into the conditions that prevailed moments after the Big Bang and help us piece together the history of our cosmos. As we continue to probe the depths of space, cosmic strings remind us that the universe is filled with mysteries waiting to be unraveled. Up next, we'll tackle another profound question. Why is there more matter than antimatter in the universe? Now turning to one of the most baffling puzzles in the universe, let's delve into why there's more matter than antimatter. According to the Big Bang theory, matter and antimatter should have been created in equal amounts at the birth of the cosmos. Antimatter is essentially the mirror image of matter particles with the same mass but opposite charge. When matter and antimatter meet, they annihilate each other, releasing pure energy. So, if equal amounts were produced, why didn't they completely destroy each other, leaving behind nothing but a void? This mystery is known as the matter-antimatter asymmetry problem. Somehow, a tiny imbalance occurred, allowing matter to dominate and form the stars, galaxies, and everything we see around us today. Scientists estimate that for every billion particles of antimatter created in the early universe, there were 1,000,001 particles of matter. That minuscule difference was enough to shape the cosmos as we know it. So, what caused this imbalance? One leading theory is a process called charge parity violation, which suggests that the laws of physics might treat matter and antimatter slightly differently. Experiments such as those conducted with particle accelerators have found evidence of small asymmetries in the behavior of certain particles. However, these discrepancies are far too small to fully explain the dominance of matter in the universe. Another possibility involves the role of neutrinos, elusive particles that rarely interact with matter. Some theories propose that neutrinos might have played a key role in tipping the scales, but this remains unproven. The search for answers continues, with scientists exploring everything from high-energy physics to the properties of the early universe. Understanding why matter prevails over antimatter isn't just an academic exercise, it's crucial to explaining the very existence of our universe. Without this imbalance, there would be no galaxies, no planets, and no life. As we unravel this mystery, we move closer to understanding the fundamental forces that shaped everything around us. Next, we'll explore another elusive particle, the neutrino, and its mysterious properties. As we venture into the next cosmic enigma, let's focus on one of the most mysterious particles in the universe, the neutrino. Neutrinos are tiny, almost massless particles that are incredibly difficult to detect because they rarely interact with matter. In fact, trillions of neutrinos are passing through your body every second, and yet you'd never even notice them. These ghostly particles are produced in abundance by stars, supernova, and even nuclear reactions here on Earth. So why are neutrinos so important? For one, they play a critical role in the life cycle of stars. During a supernova, for example, neutrinos carry away most of the energy released in the explosion, shaping the remnants of the star. But beyond that, neutrinos might hold the key to understanding some of the deepest questions in physics. One of the biggest mysteries surrounding neutrinos is their ability to change types or flavors as they travel through space. This phenomenon, known as neutrino oscillation, suggests that neutrinos have mass, a discovery that has already forced scientists to revise the standard model of particle physics. Yet the true nature of neutrinos remains elusive. Are they their own antiparticles? Could they explain the matter-antimatter asymmetry we discussed earlier? Some theories even propose that neutrinos might be connected to dark matter, the invisible substance that makes up most of the universe's mass. To answer these questions, scientists are conducting groundbreaking experiments, such as detecting neutrinos from distant supernova or studying them in massive underground detectors. Understanding neutrinos could unlock entirely new realms of physics, shedding light on everything from the behavior of the cosmos to the fundamental laws of nature. As we continue to probe these enigmatic particles, we inch closer to unraveling the secrets of the universe. Next, we'll tackle another profound challenge: the quest to unify quantum mechanics and general relativity through the theory of quantum gravity. Now, as we shift our gaze to the next cosmic puzzle, let's explore one of the most profound challenges in modern physics, the quest to understand quantum gravity. At the heart of this mystery lies the clash between two of science's most successful theories, quantum mechanics, which governs the behavior of the very small, and general relativity, which describes the force of gravity on cosmic scales. While both theories have been incredibly accurate in their own domains, they seem fundamentally incompatible when it comes to understanding the universe as a whole. So, what's the problem? Quantum mechanics deals with particles and forces at the tiniest scales, using probabilities and uncertainties. General relativity, on the other hand, paints gravity as the curvature of space-time caused by mass and energy. But when we try to apply these ideas to extreme situations like the center of a black hole or the moment of the Big Bang, our current theories break down. This is where quantum gravity comes in. It's the attempt to create a unified framework that can explain gravity in the quantum realm. One of the leading approaches to this challenge is string theory. This theory proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings can oscillate in different ways, giving rise to all the particles and forces we observe. String theory also suggests the existence of extra dimensions beyond the three we're familiar with, which could help reconcile quantum mechanics and general relativity. However, string theory is still highly theoretical, and it's yet to be proven by experiments. Another fascinating approach is loop quantum gravity, which reimagines space-time itself as a network of tiny, interconnected loops. Instead of being smooth and continuous, space-time will be quantized, broken into discrete units. This theory offers a way to describe gravity at the quantum level without relying on strings or extra dimensions. But like string theory, it remains untested, and scientists are still working to bridge the gap between these ideas and observable phenomena. The pursuit of quantum gravity is more than just an academic exercise, it's a journey to uncover the deepest truths about the universe. If we can crack this code, it could revolutionize our understanding of everything from black holes to the very fabric of reality. Yet, the path forward is far from clear. It will require not only groundbreaking experiments, but also a shift in how we think about the cosmos. With this in mind, we move to our next question, which delves into the explosive mysteries of gamma-ray bursts. Shifting our focus to another cosmic phenomenon, let's dive into the enigmatic world of gamma-ray bursts. These are among the most powerful and explosive events in the universe, releasing more energy in a few seconds than our sun will emit in its entire lifetime. Yet, despite their immense power, their origins remain one of the greatest mysteries in astrophysics. Gamma-ray bursts were first discovered in the late 1960s by satellites designed to detect nuclear explosions. Instead, they picked up intense flashes of gamma rays coming from deep space. These bursts are so fleeting, lasting from milliseconds to a few minutes, that capturing them in real time is a race against the clock. But what causes them? Scientists have identified two main categories: long gamma-ray bursts and short gamma-ray bursts. Long gamma-ray bursts, which last more than 2 seconds, are thought to be linked to the collapse of massive stars into black holes. When a star much larger than our Sun runs out of fuel, its core collapses under its own gravity, triggering a supernova. If the conditions are right, this collapse produces jets of gamma rays that shoot out at nearly the speed of light. These jets, when pointed toward Earth, are what we detect as a gamma-ray burst. Short gamma-ray bursts, on the other hand, are believed to originate from the collision of two neutron stars or a neutron star and a black hole. When these incredibly dense objects spiral toward each other and merge, they release a tremendous amount of energy in the form of gamma rays. This process also creates gravitational waves, which have been detected by observatories like LIGO, providing crucial evidence for this theory. Despite these insights, many questions remain. Why do some massive stars produce gamma-ray bursts while others don't? What exactly happens during the milliseconds of a short burst, and how do these events shape the universe around them? The study of gamma-ray bursts not only helps us understand these cataclysmic events, but also offers clues about the early universe, the formation of black holes, and the behavior of matter under extreme conditions. As we continue to observe and analyze these bursts, new mysteries emerge, reminding us just how much we have yet to uncover about the cosmos. With that, we turn to our next question, which takes us to the very boundaries of space and time. Now turning to the vastness of the cosmos, we come to a question that has puzzled scientists and philosophers alike. Is the universe infinite? This question goes to the very heart of our understanding of space and existence. At first glance, it might seem impossible to comprehend something without boundaries, but let's break it down. The universe as we know it is unimaginably large. When we look out into the night sky, we're seeing light that has traveled billions of years to reach us. But does it go on forever, or is there an edge, a boundary where the universe simply stops? The truth is, we don't know for sure. Scientists have been debating this for decades, and while we've made progress, the answer remains elusive. One of the biggest challenges in answering this question is the way we observe the universe. We can only see as far as light has had time to travel since the Big Bang, about 13.8 billion years ago. This is called the observable universe, and it's just a tiny fraction of what might exist beyond. But is there more beyond that? If the universe is infinite, it would mean that no matter how far you traveled, you'd never reach an end. On the other hand, there are theories that suggest the universe could be finite but unbounded. Imagine the surface of a balloon. It has a finite area, but if you were an ant walking on it, you'd never find an edge. The universe could be something like that, just in 3 dimensions instead of 2. This idea ties into the concept of the universe's shape, which could be flat, spherical, or even saddle-shaped, depending on the distribution of matter and energy. Another challenge is the role of dark energy, the mysterious force driving the universe's accelerated expansion. If dark energy continues to dominate, the universe could keep expanding forever, potentially becoming infinite in size. But if there's a limit to this expansion, the universe might eventually stop growing, suggesting a finite nature. So, is the universe infinite? The honest answer is that we're still searching for clues. Every observation we make, from the cosmic microwave background to the distribution of galaxies, brings us a little closer to understanding. But for now, the question remains one of the great mysteries of space, a reminder of how much we have yet to discover. With that, we move to our next question, exploring the origins of another cosmic enigma. Now shifting our gaze to another perplexing cosmic phenomenon, let's explore the mystery of cosmic rays. These high-energy particles, zipping through space at nearly the speed of light, have baffled scientists for over a century. Where do they come from? And why, despite decades of research, do their origins remain shrouded in mystery? Cosmic rays are not actually rays of light, but rather particles, mostly protons, along with some heavier atomic nuclei, that travel through space with immense energy. When they collide with Earth's atmosphere, they create cascades of secondary particles which we can detect on the ground. But tracing these particles back to their source is incredibly challenging. The problem lies in their journey through space. Cosmic rays are charged particles, which means they're deflected by magnetic fields as they travel. This makes it nearly impossible to pinpoint exactly where they came from. So, where do scientists think these particles originate? One leading theory points to supernova, the explosive deaths of massive stars. These violent events can accelerate particles to incredible speeds, potentially creating cosmic rays. However, not all cosmic rays match the energy levels expected from supernova, suggesting there's more to the story. Other possible sources include active galactic nuclei, where supermassive black holes unleash enormous amounts of energy, and even gamma-ray bursts, some of the most energetic events in the universe. Yet none of these fully explain the full spectrum of cosmic rays we observe. Adding to the mystery is the discovery of ultra-high-energy cosmic rays, particles with energies millions of times greater than those produced in human-made particle accelerators. These extreme particles are so rare and powerful that their sources are even harder to identify. Some theories suggest they might come from exotic objects like magnetars, neutron stars with incredibly strong magnetic fields, or even from processes we haven't yet discovered. Despite the challenges, scientists are making progress. Observatories like the Pierre Auger Observatory in Argentina and the Ice Cube Neutrino Observatory in Antarctica are working to detect and study these particles, hoping to unravel their origins. Yet, for now, the source of cosmic rays remains one of the most enduring mysteries in astrophysics, a testament to the complexity and wonder of our universe. As we continue to probe this enigma, we're reminded that every discovery brings us closer to understanding the cosmos and our place within it. Now, delving into one of the most profound mysteries, let's ponder the boundaries of space and time. What are they, and do they even exist in the way we imagine? These questions have puzzled philosophers and scientists alike for centuries, and yet we're still grappling with their true nature. At first glance, space and time seem like fundamental aspects of our reality. Space is the stage where everything unfolds, and time is the measure of its progression. But is it really that simple? Modern physics suggests that space and time might not be as basic as we think. Instead, they could be emergent properties, phenomena that arise from more fundamental processes. For example, some theories propose that space and time emerge from the interactions of tiny, discrete units at the quantum level, much like how temperature emerges from the motion of atoms. Einstein's theory of general relativity revolutionized our understanding of space and time, showing that they are intertwined in a single fabric called spacetime. This fabric can be warped by massive objects, creating what we experience as gravity. Yet, general relativity doesn't explain what happens at the smallest scales, where quantum mechanics takes over. This raises the question, are space and time continuous, or do they exist in discrete chunks at the tiniest levels? Another intriguing idea is that space and time might have boundaries, limits beyond which they cease to exist. For instance, at the edge of a black hole, spacetime appears to break down into what physicists call a singularity. Here, our current laws of physics fail, leaving us with more questions than answers. Similarly, the Big Bang suggests that both space and time had a beginning. But what existed before? Did space and time emerge from nothing, or are they part of a larger, more complex framework? Philosophers have also weighed in, debating whether space and time are absolute or relative. Do they exist independently of the objects within them, or are they simply constructs of our perception? These questions challenge our very understanding of reality, pushing us to rethink the nature of existence itself. As we continue to explore these boundaries, we're reminded that the universe is far more intricate than we can currently comprehend. Whether space and time are fundamental or emergent, finite or infinite, one thing is certain: unraveling their mysteries will deepen our understanding of the cosmos and our place within it. With every new discovery, we step closer to answering one of the most profound questions in science and philosophy. Now, as we approach the final and perhaps most profound question of our journey, let's contemplate the ultimate nature of reality. What is the true fabric of existence? This question has been at the heart of philosophy, science, and even spirituality for as long as humanity has sought to understand the universe. And yet, the more we explore, the more elusive the answer seems to become. At its core, reality appears to be composed of the physical world around us, matter, energy, and the forces that govern them. Quantum mechanics has revealed a bizarre and unpredictable layer beneath this seemingly solid reality. At the quantum level, particles exist in states of probability, appearing and disappearing in ways that defy our everyday experiences. This has led some to suggest that reality itself might be a kind of quantum construct, a tapestry woven from uncertainty and possibility. But what about consciousness? Some theories propose that reality is not just an external, objective phenomenon, but something deeply intertwined with the mind. The idea that consciousness plays a fundamental role in shaping reality has gained traction, particularly in interpretations of quantum mechanics. Could it be that the universe only becomes real when observed? This leads to even more questions. Is reality a shared experience, or does it differ from one observer to another? Then there's the concept of simulation theory, which suggests that our reality might be a highly advanced simulation created by a more intelligent civilization. While this idea may sound like science fiction, it's a hypothesis that some scientists and philosophers take seriously. After all, if we're able to create increasingly complex virtual worlds, could it be possible that we ourselves are living in one? Beyond these theories lies the possibility that reality is something we can't fully comprehend with our current knowledge. String theory, for example, posits that the universe is made up of tiny, vibrating strings existing in multiple dimensions we can't perceive. Similarly, the idea of a multiverse suggests that our reality might be just one of countless others, each with its own set of physical laws. As we grapple with these ideas, one thing becomes clear: the ultimate nature of reality might be beyond the reach of our current understanding. But that doesn't mean we should stop seeking answers. With each new discovery, we inch closer to unraveling the mysteries of existence, reminding us that the universe is far more wondrous and enigmatic than we can imagine. And as we ponder these questions, we're reminded that the journey of exploration is just as important as the answers we seek. As we bring this cosmic journey to a close, let's take a moment to reflect on the 20 mind-bending questions about space that continue to baffle scientists, philosophers, and curious minds alike. From the mysteries of dark matter and dark energy to the enigmatic nature of black holes and the possibilities of parallel universes, each question invites us to explore the boundaries of our understanding. These questions aren't just abstract curiosities, they shape the very foundation of how we perceive the universe and our place within it. What's truly remarkable is the ongoing effort to find answers. Scientists around the world are probing the cosmos with cutting-edge technology, from powerful telescopes to particle accelerators, in the hopes of unraveling these cosmic enigmas. Yet, with every discovery, new questions emerge, reminding us that the universe is vast, complex, and endlessly fascinating. Now we turn to you. What are your thoughts on these questions? Do you have a favorite mystery that captivates your imagination, or perhaps a theory you'd like to share? Let us know in the comments below. Your insights and perspectives add richness to this ongoing exploration of the cosmos. If you've enjoyed this journey through the mysteries of space, don't forget to subscribe and hit the notification bell to stay updated on more cosmic explorations. The universe is full of wonders waiting to be discovered, and we're just getting started. Let's keep exploring together.